Hello, I'm John Waldron, and I teach in the Earth Science programs here at the University of Alberta. And I'm standing in the Geoscience Garden. This is an outdoor facility that we can use as an outdoor museum, and we can also use it for teaching. In Edmonton, we have the beautiful valley of the North Saskatchewan River flowing through the city, and we can use that for field trips where we can show you things that have happened in the last 70 million years or so of Earth history, going back to the end of the dinosaur age. But if we want to see things that have gone on in Earth history earlier than that, the more ancient parts of the evolution of the planet, we would need to go west to the mountains or east to the Canadian Shield, and those places are difficult to get to during term time. So in the Geoscience Garden, we have a collection of rocks that are placed so as to tell the story of the evolution of the Earth crust in Western Canada. And we can visit these during our classes and learn to make measurements, make observations, as we would be if we were able to take field trips to those places. We brought together rocks that represent the Canadian Shield, the Western Canada Sedimentary Basin, and the Canadian Cordillera, the mountains that lie to our west. The rock I'm standing next to is a unit called the Cairn Formation. You can see this rock unit in the mountains near Canmore. It's actually a reef limestone, and you can tell that because you can see the remnants of fossil sponge-like organisms in here, and you can see the holes in the rock that represent the cavities in an ancient reef. This is a very important rock type for the history of Alberta because in rocks like this, where they're buried beneath the plains, oil was discovered in the Leduc area in the mid-20th century, and that became very important in the history of oil exploration in central Alberta. So let's walk eastwards in the Geoscience Garden, and as we walk this way, we're going to be walking past older and older rocks. Here we are in the eastern part of the Geoscience Garden, and these rocks represent the Canadian Shield, going back 3 billion years and before. So here we're in the part of the Geoscience Garden that represents the oldest rocks in the Canadian Shield. And I'm looking at what is actually one of the most common rock types in the continental crust. This is a granite. And we can tell by looking closely at the granite, we can see all the mineral grains that it's composed of. These are all very common minerals: quartz and feldspar and mica. There's maybe a little bit of a mineral called hornblende in this granite as well. It represents a really common part of the Earth's continental crust. I'm going to walk on now because we have something different over here. This is a much darker rock than the last one, and it's also a much finer grained rock than the last one. This is a basalt. It represents a lava that came out of a volcano probably 3 billion years ago, in this case, very early in the history of Western Canada. And one thing that's interesting here is these veins here, which are filled with granite, similar to the rock that's behind me. So that suggests that these rocks are even older than the granite, and the granite magma, which is molten material, was intruded into the Earth's crust after this basalt had formed. So it's by making observations like this that we can figure out the order of events in the history of a particular part of the Earth's crust. In addition to the common rock types like granite and basalt, we have some unusual rock types as well. So this, like the granite, is an igneous rock formed by magma that solidified within the Earth's crust, but it produced this beautiful blue mineral, which is sodalite. And it's an example of a type of igneous rock called syenite, much less common than granite, but a beautiful example of what's known as an alkaline igneous rock. Now we're going to walk westward past some more outcrops of granite and basalt, and eventually we come to some rocks which are obviously layered. So these represent typical sedimentary rocks formed by deposition of particles on the Earth's surface. So these rocks in the middle part of the Geoscience Garden are clearly layered, and they are sedimentary rocks that are representative of what we find in the Western Canada Sedimentary Basin. It's actually these kinds of rocks that underlie Edmonton, that are buried beneath the city. They're clearly layered, and on the top surface of this rock, when we look a little bit closer, we can see that on the top of the layer there's a whole series of ripples, and those ripples are made when currents flow over the seafloor or over a riverbed or a lake floor, and they clearly tell us something about the environment when these rocks were being deposited. And these are some of the kinds of things that rocks can teach us about ancient environments. I'm going to go over a little bit to the northwest, where there's a rather different looking sedimentary rock. It's grey, and we'll walk over and have a look at it. And it's a little bit older than this one, and it has some more clues about the environment that existed in the Edmonton area in the past. So let's take a walk over and see what we can see. So when I look closely at this rock, I can see some fossils. So here on this surface, all arranged along a particular layer, are small fossil corals. And these rocks come from the Mississippian period. They're probably about 340 million years old. And during that time, Western Canada was covered by a warm tropical sea in which these corals flourished and in which this limestone was deposited. As we look to the west in this part of the Geoscience Garden, we will be traveling further and further into the mountains, where we will be looking at rocks that have been brought up from deeper and deeper within the earth. So let's head off to the west and see what we find. As we go west, we pass other kinds of sedimentary rock, including one that's made of pebbles that are easily visible. This is an example of conglomerate. It was deposited by a fast-moving river system back in the Cretaceous period. And we pass some layers of volcanic ash here, also from the Cretaceous period, which show that during this time volcanoes were active in our part of the earth. Those probably record the movements of the plates that were going on just off the coast along the Pacific margin of North America, where plate movement is still active at the present day. Continuing on from the volcanic ash, we begin to get into rocks which show signs of the deformation that forced up the mountains that dominate Western Canada. And in this rock you can see some of the effects of the deformation from about 200 million years ago up until about 60 million years ago. When we get close to this rock, we can see that it clearly still has sedimentary layers running through it, but something has happened to it. During the building of the mountains that dominate Western Canada, this rock has been squeezed. And as a result of that squeezing, we can see that the layers within the rock are curved, they've been folded, and the rock has a new fabric, as we say. It splits in this direction, perpendicular to how it was squeezed, and that new fabric has made this rock into a slate. It's a metamorphic rock, and this is a testament to some of the forces at play in the building of the mountains and the uplift of these rocks, which come from quite deep down. They're quite old sedimentary rocks, originally sedimentary rocks, now metamorphosed. We go further west within the mountains, we can come to rocks that have been brought up from even deeper down within the earth crust. Here we are nearly at the western extremity of the Geoscience Garden, and this rock represents some of the deepest parts of the Earth's crust, brought up to the surface during the process of mountain building, which has enabled Earth systems to remove enormous amounts of rock from off the top by weathering and erosion. And that leaves us with rocks that have minerals that form very deep within the Earth's crust. When we look closely at this rock, we can see that it has grey feldspar in it and black hornblende. Those are minerals we've seen before. And then this pink mineral that is all through the rock is garnet. And that garnet formed probably between 10 and 20 kilometers down within the Earth. And its chemical composition and mineral structure tells us something, again, about the conditions in which this rock formed. So all through the Geoscience Garden, we can look at rocks and collect evidence for the environment in which rocks formed in the past, whether it was on the ocean floor or deep within the Earth's crust. The final rock I'll take you to is actually a very recent one. It's the youngest rock in the Geoscience Garden, and it represents what's going on at the margin of the Pacific Ocean at the present day. So let's go and have a look. So these rocks mark the end of our tour. These are the youngest rocks in the Geoscience Garden, and looking at them from a distance, they have some layers in them. You might think they were sedimentary rocks, but when we get up close, we find that this is a harsh, scratchy rock. It's full of holes, and when we look at it closely, we find it's actually made of glassy material. And this is actually a lava. It's a lava that came out of a volcano, probably in the last few thousands or tens of thousands of years. So it was a frothy lava that was full of gas bubbles, and it solidified to make this very lightweight, scratchy rock. And this is actually an example of pumice. It's a kind of lava that is so full of gas bubbles that it weighs much less than most rocks. And in fact, some samples of pumice will actually float on water. So although some of these boulders are quite large, they were amongst the easiest to move into position in the Geoscience Garden because they're much lighter in weight than the other rocks. So we find volcanoes along the west coast of North America. Probably Mount St. Helens is the most famous of those volcanoes, but there are others, and they all represent the effects of plate movement, which is continuing until the present day and will continue millions of years into the future, so far as we know, as the Pacific plate moves past North America. So right up to the present day, we can see rocks that are recording the processes going on both within and at the surface of the Earth. So we hope you've enjoyed this tour through the Geoscience Garden. Hopefully you can come and experience it for real. And when you do, you'll find there are some resources on the web that you can consult. We have little QR codes on the plaques that accompany many of the rocks, and those will take you to a website where you can learn more about the history of the different rocks that make up the Geoscience Garden, and which tell the story of the evolution of the western part of the North American continent where we live.